to fill the last 16 minutes of our lecture. A bit of abstraction again, both abstraction and specifics. Back to talking about random systems and stochastic variables that express a random system, you could say. We talked in general terms by distribution function and density function, and then we saw 3 specific examples of such systems and models for systems. Back to the general way of thinking a little bit. Standing in front of a system, there could be different features of the system that you would be interested in. Something that people are very often interested in when you're facing a random system is sort of the average level of what happens, right? What is going on? How often is it going to happen on average? How many patients on average will there be here? How many on this on average? So the mean of a system can technically be explicitly defined like this, where we take a system and say, we take each individual possible outcome in the system and we multiply the probability of this outcome. This is also, you could say x in all possible outcomes, x times the probability of the outcomes in this discrete world that we are in today. We can express it like this. For instance, if it's a symmetric toss with dice, for instance, there is like 1/6 chance for each of the 6 outcomes. You take 0 times 1/6, 1 times 1/6, blah, 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 and you take the average, which would then just be the average of O up to 6. That would be, not O, you cannot get a 0 with a dice. You can get 1, 6, 2, 5, 3, 4, all of these adds up to 0, to 7, god damn it, and the average of those are 3.5. So the mean in such a system would be 3.5. Then you could also calculate the mean in an asymmetrical system if you have cheating dices also, just by using the weights by each of the probabilities, by this definition here. It makes pretty good sense, I hope. So given an arbitrary random system, you could use the probabilities of each of the event to say on average what will happen. So if something happens quite rarely, it will not have a large influence of the mean, but if it happens quite often, it will influence the mean in a reasonable way. I hope you can follow me this far, because the next one is slightly more abstract, but even more important. Related to my comment last time, where we were a bit more simple-minded, on real data in an Excel sheet, we calculated the mean and we calculated the variance. Just looking at the numbers, there was empirical formulas for doing that. What I'm showing you here are abstract formulas in the theoretical world, telling you that if we have a model system, we can do the same thing within the model. If we have the probabilities, we can find out what is the mean and what is the, which is on the slide now, what is the theoretical variance of a system. That could be very interesting to know in a system, not only how often are things going to happen, but how different is it going to be from day to day, for instance. I mean, what is the variability of the system? And if we know the probabilities of the system, we can find the variability. Because we can take each individual outcome and see what is the difference of each individual outcome to the mean of the system. Then we can square this, we can weigh with the probabilities, and we can add together. So this is like a weighted mean of square deviances. It's a weighted mean of square deviances. And that is the theoretical definition of a variance in a discrete system. So mean and variance exist not only as computational formulas for data, it exists as theoretical definitions in probability systems. That's pretty neat to have this thing going on, actually. This means, and I'm going to do this very rapidly, you could look at the extra math if you want to go into detail of this, extra math things that I share with you. This means that we could actually try and play around with the known distributions and plug the known distributions into these formulas, using the formulas for the probabilities, and see what happens. Given that we have a mathematical formula for the system, which we have in those 3 cases, that is still a bit abstract, but not extremely extrapolable. At least we have a mathematical formula for each model. If we do this exercise, it's a mathematical exercise. It's not so difficult if you have a bit of math skills. But I'm not going to do it here. I'm just going to tell you. Then you would find out what is the mean in a binomial system. The mean is NP. I think we all would know that, actually. If I throw 100 times with a coin and the P is 0.5, I expect 50 outcomes on average. If I do it 1,000,000 times, right? That is what the formula is expressing. What is maybe less familiar is that there's also a variability. I don't expect exactly 50 out of 100 each time. Sometimes it'll be above, sometimes it'll be below, of course. That's the natural variability. We would not be surprised of that. But maybe we wouldn't know how large would this variability be, sort of, if I average, I do it a lot of times. Well, here's the formula. Binomial variance formula. NP, 1 minus P. So these can be found, and we're going to use that a little bit throughout. Similarly, you could find the formulas for the hypergeometric. I'm simply going to jump this now, not going to dig into it. The formulas are there for finding the mean and the variance of the hypergeometric, and the formulas are there to find the mean and the variance of the Poisson distribution. These are nicely simple. The intensity lambda is both the mean and the variance in the Poisson system. That's a neat thing. Anyway, that was a short going through the concept of mean and variance in probability systems. Abstract and in the specific distributions. Let's, George, turn to the final